please subscribe to support the channel. There's a diamond floating in space, bigger than Earth's moon. It's not a myth or a metaphor, but a real celestial body, the crystallized heart of a dead star. Far beyond our solar system drifts a gem so massive it could outshine every diamond ever found on Earth combined. Once a brilliant sun, it burned through its fuel, died, and cooled over billions of years until its carbon core solidified into an enormous cosmic diamond. Suspended in the endless dark, it glimmers faintly, silent, eternal, and unimaginably vast. A reminder that even when stars die, they can leave behind something dazzlingly beautiful. The star that holds this unimaginable diamond has a name that might sound dry at first: BPM 37093. On paper, it's a catalog designation, a technical label assigned by astronomers cataloging variable stars. But behind that string of letters and numbers lies a story that merges science, music, and the human desire to connect with the cosmos in ways that feel almost poetic. BPM 37093 is more than a catalog entry. It's a star with personality, a cosmic relic that has captured imaginations because of what it represents: a diamond the size of a moon. To make it a little more approachable, astronomers affectionately nicknamed it Lucy, inspired by the famous Beatles song, "Lucy in the Sky with Diamonds." The connection is not accidental. Just like the song evokes glittering imagery of sparkling dreams and floating visions, this star literally embodies a diamond in the sky, turning a whimsical metaphor into a tangible astronomical reality. Lucy's name bridges the gap between science and culture. In a way, it serves as a reminder that human beings are not merely observers of the universe. We are storytellers. By giving this star a nickname linked to art, astronomers have allowed it to exist not only in the annals of astrophysics, but also in the collective imagination. People who may not understand the complex physics behind white dwarfs can still marvel at the idea of a diamond the size of a moon silently orbiting in the galaxy, a symbol of cosmic beauty and scale. The name Lucy has a resonance that BPM 37093 alone never could achieve. It's memorable, playful, and immediately evokes the wonder that comes with the realization that the universe has creations more extravagant than anything on Earth. At the same time, the official designation BPM 37093 carries its own significance, grounding Lucy firmly in scientific research. The BPM comes from the Bruce Proper Motion Survey, a Harvard-Smithsonian project that cataloged variable stars, assigning each a unique number for identification. BPM 37093 is thus a point on a map of the stars, a mark of human curiosity and an object of intense study. This dual identity, one whimsical, one scientific, mirrors the nature of Lucy herself. She is both beautiful and precise, a reminder that the universe can be understood through reason, yet still inspire awe beyond comprehension. The nickname makes her relatable, while the catalog name makes her measurable, bridging the poetic and the empirical in one extraordinary celestial object. The choice of Lucy also serves as a subtle celebration of the way humans experience the cosmos. In popular culture, diamonds are symbols of rarity, value, and beauty. By likening a star to a diamond through a cultural reference, astronomers effectively translate an abstract scientific phenomenon into something everyone can visualize and appreciate. Imagine the Beatles' lyrics floating through your mind, and now imagine that those whimsical, glittering images have a real-life counterpart 50 light-years away. That's Lucy, the marriage of imagination, music, and astronomy. A diamond in the sky in more than just the literal sense. It's as though the universe itself conspired to create a poetic symbol of endurance and beauty, one that reflects light from billions of years of stellar evolution while also sparking wonder in our modern human consciousness. Lucy is not just a static object in the sky. Her name hints at a journey through both space and time. As astronomers study her, They traced back billions of years to the life of a star that once shone brightly before exhausting its nuclear fuel. Every pulsation, every measurement of her crystallized core tells a story of stellar evolution, endurance, and transformation. Naming her Lucy, with all the cultural baggage of sparkle, value, and wonder, emphasizes the idea that science is not separate from human emotion or creativity. It is a collaboration between observation and imagination, where a seemingly cold, distant star can resonate with the hearts and minds of people across the globe. By introducing Lucy with both her catalog designation and her nickname, astronomers set the stage for a narrative that is as much about human curiosity as it is about cosmic phenomena. BPM 37093 is not merely a point of light in the constellation Centaurus. It is a testament to what we can discover when we combine rigorous observation with a willingness to dream. Her dual identity serves as a bridge. She exists in the meticulous calculations of astrophysicists, in pulsation data, in spectra, and models. But she also exists in the imaginations of anyone who looks up at the night sky and wonders about the unimaginable treasures that might be out there. Lucy, a diamond star, captures both the precision of science and the poetry of existence. As we begin to understand her position, her composition, and the incredible story of her crystallized core, it becomes clear that Lucy is more than a nickname or a catalog entry. She is a symbol of the universe's creativity, a cosmic artifact that blends art and science. Her name is an invitation to look deeper, to explore how stars live and die, and to realize that the universe is capable of producing wonders far beyond our everyday comprehension. From this moment, whenever we speak of Lucy, we're acknowledging not just a white dwarf or a crystallized carbon core, but a phenomenon that connects human imagination, culture, and the immense scale of space. Lucy drifts silently about 50 light-years from Earth, nestled in the heart of the constellation Centaurus, one of the most prominent and striking star patterns visible in the southern sky. Centaurus itself is an ancient symbol in mythology, representing a centaur, a creature that is half man, half horse, a fitting backdrop for a star that bridges the realms of reality and imagination. For observers on Earth, with clear southern skies, Centaurus spreads broadly, encompassing some of the brightest stars visible to the naked eye, such as Alpha Centauri, our closest stellar neighbor. Yet Lucy remains hidden from casual stargazing, her subtle glow lost amidst the brilliance of younger, more luminous stars. She is quiet, unassuming in brightness, but extraordinary in essence, holding within her the largest diamond in the cosmos. Being 50 light-years away places Lucy relatively close in astronomical terms, though the scale is still almost incomprehensible to the human mind. Light from Lucy takes half a century to reach Earth, meaning that the photons we see today left her more than 50 years ago. That's longer than a human lifetime, yet a blink in the life of a star. This distance allows astronomers to study Lucy in remarkable detail using advanced telescopes and techniques, yet it also underscores the loneliness and remoteness of such a celestial wonder. To travel to Lucy at the speed of modern spacecraft would take tens of thousands of years, a journey impossible with our current technology, emphasizing her existence as a distant treasure, untouchable but observable. Lucy's location in Centaurus also provides context for her discovery. Centaurus is a constellation rich with scientific interest, hosting not only nearby stars, but also intriguing stellar phenomena, such as binary systems, variable stars, and dense star clusters. Lucy's position within this constellation allowed astronomers to study her light and pulsations in relation to the surrounding stars, using the predictable backdrop of Centaurus as a celestial reference frame. Her discovery was not random, but the result of meticulous surveys targeting variable stars, stars whose brightness subtly changes over time. By focusing on this region, scientists could detect the minute pulsations that would eventually reveal Lucy's secret, that she is a crystallized white dwarf, a diamond star in the literal sense. When we consider her distance and placement, it becomes even more remarkable how much we have learned about Lucy. Using Earth-based telescopes and space observatories, astronomers have been able to measure not just her brightness, but her pulsations, temperature, and composition, all from 50 light-years away. Each observation requires careful calibration, as her light must travel through the interstellar medium, dimmed and scattered along the way. Despite these challenges, scientists have managed to unlock her secrets, showing that even at such distances, the universe can communicate its most intricate details to those who listen carefully. Lucy's location is not just a set of coordinates in space. It is the stage upon which the story of a cosmic diamond unfolds, a fixed point in the galaxy from which we can observe the laws of physics playing out on a scale beyond imagination. Lucy's position also has symbolic resonance. Situated in Centaurus, a constellation historically associated with wisdom and knowledge, thanks to its centaur figure, often linked to the mythical Chiron, the healer and teacher, Lucy seems almost fated to inspire learning and curiosity. Her light, traveling across decades to reach us, carries with it lessons about the life cycles of stars, the forces that govern their transformation, and the ultimate fate of objects like our own sun. Even though she lies tens of trillions of kilometers away, her presence is immediate in the sense that her story informs and enriches human understanding, connecting our world to the vast cosmic neighborhood we inhabit. The more we focus on Lucy's place in the sky, the more we appreciate the subtlety of her brilliance. Unlike a massive supernova or a bright young star, she does not dazzle with raw energy. Instead, her presence is quiet, almost meditative. She is a diamond, not a fireball, and her beauty lies in composition, structure, and history rather than sheer luminosity. She reminds us that some of the universe's most extraordinary wonders are hidden in plain sight, requiring patience, technology, and imagination to uncover. Being located in Centaurus gives Lucy context within the tapestry of the night sky, yet it also allows her to stand apart, a cosmic treasure quietly shining, awaiting discovery and admiration. Her position also sets a stage for understanding her relationship to other stars. At 50 light-years away, Lucy is close enough for detailed analysis, but far enough to emphasize the scale of stellar evolution. Nearby stars provide reference points for measuring her properties, and Centaurus's rich stellar population enables astronomers to place Lucy within a broader cosmic timeline. By comparing her characteristics with other white dwarfs and main sequence stars in the constellation, scientists have been able to estimate her age, her temperature, and even the processes that led to her crystallization. Her placement is therefore not just spatial, but scientific, a key node in the web of astrophysical knowledge that allows us to study the life cycle of stars and understand the future of our own sun. In summary, Lucy exists 50 light-years away in Centaurus, hidden among brighter stars yet extraordinary in what she represents. She's close enough for us to measure her, yet her distance preserves her mystery. She occupies a quiet, elegant corner of the galaxy where the forces of stellar evolution have crafted one of the universe's most astonishing objects. Understanding her location is the first step in grasping the full scale of what she is, a diamond star. Ancient, immense, and luminous in a way that transcends mere brightness. By situating Lucy in the cosmos, we begin to appreciate the interplay of distance, context, and observation that allows humanity to uncover even the most hidden marvels of the universe. Lucy is what astronomers call a white dwarf, the final evolutionary stage of stars like our sun. Unlike the blazing, life-filled stars we see in the night sky, white dwarfs are the remnants of stellar life. Dense, dim, and extraordinarily compact. They're not active in nuclear fusion anymore. Instead, they glow faintly as they slowly release the heat left over from their earlier lives. Lucy, specifically, represents a fascinating and rare subclass of white dwarfs, one whose core has crystallized into a diamond-like structure, a process that turns her from an ordinary stellar corpse into a cosmic jewel. To understand Lucy, we need to grasp what it means to be a white dwarf. how such objects form, and why they are significant in the broader story of stellar evolution. A white dwarf is essentially a star stripped to its core. When a star exhausts the hydrogen fuel at its center, it can no longer sustain the nuclear reactions that create outward pressure to balance gravity. For stars roughly the size of our Sun, this triggers a series of transformations that ultimately lead to the formation of a white dwarf. As the star swells into a red giant and sheds its outer layers, the remaining core, extremely hot, incredibly dense, and composed primarily of carbon and oxygen, begins its quiet existence as a white dwarf. In Lucy's case, this core, once surrounded by a brilliant stellar envelope, now floats exposed in space, a relic of a life that ended billions of years ago. She no longer fuses atoms in her core. Her energy comes solely from the slow cooling of residual heat. And it is this slow cooling over time that has allowed her carbon and oxygen interior to crystallize. The density of a white dwarf is astonishing and crucial to understanding Lucy. While she may be roughly the size of our moon, her mass is comparable to that of the sun. That means a single teaspoon of her material would weigh several tons on Earth. This incredible density results from the physics of electron degeneracy, a quantum mechanical effect that prevents the core from collapsing under its own gravity. Unlike normal stars, which maintain equilibrium through nuclear fusion, white dwarfs rely on this quantum pressure to resist total collapse. Lucy, as a crystallized white dwarf, showcases the extreme outcomes of stellar physics. A tiny, ultra-dense object that contains within it the remnants of a once massive star, now transformed into a frozen cosmic gem. Lucy's life as a white dwarf is also a story of time and patience. Unlike energetic stars that burn brightly for millions or billions of years, she exists in a slow, almost imperceptible evolution. Her light is faint, and her cooling occurs over billions of years, gradually dimming as she radiates her leftover heat into space. This quiet stage of existence might seem uneventful, yet it is precisely during this period that the most remarkable transformation occurs, the crystallization of her carbon core. The forces and conditions that allow carbon and oxygen atoms to arrange themselves into a rigid lattice only occur under immense pressure and after billions of years of cooling. Lucy exemplifies this process, turning an abstract physical theory into a tangible cosmic phenomenon. White dwarfs like Lucy also hold critical importance for astronomers. They serve as natural laboratories for studying the physics of matter under extreme conditions. By examining her mass, temperature, luminosity, and pulsations, scientists can test theories of quantum mechanics, stellar structure, and the life cycle of stars. Lucy's crystallized interior, in particular, provides direct evidence of predictions made decades ago about how white dwarfs cool and solidify over time. She is not merely a relic of the past, but a living record of stellar physics, a cosmic archive that encodes billions of years of information about the life and death of stars. Moreover, Lucy challenges our typical perception of what stars are. When we look at the night sky, we often see stars as bright points of light, endless and eternal. But Lucy, as a white dwarf, reminds us that stars are finite. They are born, they live, and they die, leaving behind remnants that may be far removed from the fiery brilliance we associate with starlight. Yet in her death, Lucy becomes something perhaps even more extraordinary than she was in life. A solid, shining diamond floating silently through space. Her transformation underscores the full arc of stellar existence, revealing that endings can hold as much beauty, wonder, and scientific significance as beginnings. In understanding Lucy as a white dwarf, we begin to appreciate the delicate interplay of physics that governs her existence. She is simultaneously a monument to the life of a star and a laboratory for extreme matter. Her quiet glow, dense interior, and crystallized structure are all hallmarks of a stage of stellar evolution that most stars, including our Sun, will eventually pass through. Lucy embodies both the inevitability of stellar death and the universe's capacity to create objects of astonishing complexity and beauty even in that death. She is a white dwarf, yes, but also a cosmic diamond, proof that the remnants of stellar life can inspire wonder as much as the living stars themselves. The journey that leads to Lucy's existence begins with the ordinary, unassuming life of a star like our Sun. Stars are born in vast clouds of gas and dust, regions known as stellar nurseries, where gravity slowly pulls material together until nuclear fusion ignites at the core. For billions of years, these stars live in a delicate balance. The pressure generated by nuclear fusion pushing outward matches the inward pull of gravity. This balance is what allows a star to shine steadily, providing heat and light. But all stars are mortal. At some point, they exhaust the hydrogen fuel at their cores, and that quiet balance tips, setting in motion a dramatic sequence that will eventually transform an ordinary star into a white dwarf like Lucy. As hydrogen becomes scarce in the core, fusion begins to slow, and the core contracts under gravity. Meanwhile, the outer layers of the star expand dramatically in response to this contraction, and the star swells into a red giant. During this phase, the star becomes enormous, hundreds of times larger than it was in its main sequence life. Its outer layers cool slightly, giving it a reddish hue, but internally, the pressure and temperature continue to rise. This is a volatile period in the star's life. The balance of forces is unstable, and the star undergoes complex fusion reactions in shells around the contracting core, creating layers of different elements. The once serene star is now a dynamic, pulsating, and massive object, slowly preparing for the next stage of its evolution. Eventually, the outer layers of the red giant become gravitationally unbound. Stellar winds, pulsations, and instability cause the star to shed its outer envelope, releasing vast amounts of gas and dust into space. This expelled material may form beautiful planetary nebulae, intricate clouds of glowing gas that can stretch light years across. For a few fleeting tens of thousands of years, a blink of an eye on a cosmic timescale, the dying star's remnants light up the surrounding space with astonishing colors and patterns. These layers drift away, leaving the star's dense core exposed, and it is this core that will become a white dwarf. Lucy, in her crystallized form, is the result of this ancient shedding, a silent monument to the furious, chaotic transformation that preceded her quiet existence. The remaining core is incredibly dense, composed primarily of carbon and oxygen, the fusion byproducts of the star's life. Without the outward pressure of fusion to counterbalance gravity, this core collapses under its own weight, compressing the material to the extreme densities characteristic of white dwarfs. In Lucy's case, this collapse didn't result in destruction, but in transformation. She became a compact, spherical object, roughly the size of the moon, yet containing a mass comparable to the sun. Her extreme density is what allows a teaspoon of her material to weigh several tons, a consequence of the same quantum mechanical principles that govern all white dwarfs. This core, once hidden deep within a massive red giant, now floats freely in space as a faint, enduring light, a star that has transitioned from life to a quiet, crystallized eternity. The formation of a white dwarf is both a violent and delicate process. The shedding of outer layers releases enormous energy and material into space, seeding the galaxy with elements that will eventually form new stars, planets, and perhaps even life. The remaining core, though tiny in comparison to the star's original size, contains the secrets of its entire lifespan, its age, composition, and internal processes. In Lucy's case, this core underwent another extraordinary transformation over billions of years. The carbon and oxygen inside it slowly cooled and crystallized into a diamond-like lattice, creating the cosmic jewel we observe today. The process of forming a white dwarf is therefore both a death and a beginning. It marks the end of a star's active fusion life, but it also sets the stage for new phenomena, new knowledge, and new marvels. Understanding how stars like our Sun die gives insight not only into Lucy's origins, but also into the future of our own solar system. In roughly 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, shedding its outer layers in a spectacular display that will reshape the solar system. Its core will contract, and it, too, will become a white dwarf. If conditions align similarly to Lucy's, the Sun's carbon-oxygen core may eventually crystallize into its own massive diamond, a distant echo of the fate that Lucy embodies. Lucy is, in essence, a glimpse into the distant future of our Sun, a frozen vision of what awaits our star once its fiery life concludes. By tracing this life cycle, from hydrogen fusion in the core to expansion into a red giant, to the shedding of outer layers, and finally to the birth of a dense, crystallized core, we begin to see Lucy not as a static object, but as the endpoint of an incredible cosmic journey. Every white dwarf carries the memory of its progenitor star, and Lucy's memory is etched into her structure, composition, and size. She is a frozen testament to stellar evolution, a quiet yet spectacular finale to processes that unfold over billions of years. The story of white dwarf formation illuminates the profound balance between destruction and creation, showing how even the death of a star can produce something awe-inspiring, endearing, and unique in the cosmos. Lucy's existence as a white dwarf is extraordinary, but what truly sets her apart from almost anything we experience on Earth is her extreme density. Density, in this cosmic context, is not just a measure of mass per unit volume. It is a physical reality so extreme that it defies everyday intuition. Lucy may be roughly the size of the Moon, about 4,000 kilometers across, but her mass is nearly equivalent to that of our Sun, over 300,000 times the mass of Earth. This means that an object that appears relatively small in comparison to a planet is in reality an almost incomprehensibly compact ball of matter. Imagine squeezing the Sun, an enormous, blazing sphere of gas, into the volume of a tiny moon. That is Lucy. The result is a density so high that just a teaspoon of her material would weigh several tons, a concept that stretches the limits of human imagination. To put this into perspective, consider everyday comparisons. A cubic centimeter of lead, one of the densest metals on Earth, weighs about 11 grams. A cubic centimeter of water weighs 1 gram. In Lucy, a cubic centimeter of her material could weigh more than a ton. Every atom is packed closely together, leaving no space between them. This extreme compression is possible due to electron degeneracy pressure, a quantum mechanical effect that allows electrons to resist being squeezed into the same energy state. In ordinary matter, the atoms are free to spread out, but in a white dwarf like Lucy, gravity has compressed the matter so intensely that the normal rules of density no longer apply. The electrons form a degenerate gas, providing the pressure needed to halt the collapse of the star. Without this quantum phenomenon, Lucy would not exist as a stable object. She might have collapsed further, possibly forming a neutron star or black hole instead. The consequences of this density are staggering. Every cubic centimeter of Lucy contains enough matter to outweigh entire skyscrapers, entire cities, or even large mountains on Earth. If you were somehow able to scoop up a teaspoon of Lucy and place it in your hand, an utterly impossible feat, of course, the weight would crush you instantly under its unimaginable mass. The very idea challenges human intuition because we are accustomed to the relative sparseness of matter in our everyday environment. Lucy's density makes her a laboratory for extreme physics, a place where the laws of nature reveal themselves in ways almost impossible to visualize. This extreme density also affects Lucy's gravity. While her overall gravitational pull is weaker than that of the Sun due to her smaller radius, the surface gravity on her is hundreds of thousands of times stronger than Earth's gravity. If an astronaut could somehow stand on Lucy's surface, ignoring the impossibility of surviving such conditions, they would be instantly flattened by the overwhelming gravitational force. Even small variations in her mass or size dramatically affect the forces at her surface, illustrating the delicate balance that allows a white dwarf to exist. The material is compressed to the edge of stability, and any additional mass could push her beyond the limit, leading to further collapse. Lucy's structure, therefore, is not merely dense, it is a cosmic tightrope act, a balance between the crushing weight of gravity and the quantum pressure that resists it. Lucy's extreme density is also central to her crystallization process, the very phenomenon that makes her a diamond star. High density allows the carbon and oxygen atoms in her core to be forced into a crystalline lattice as she cools. Under ordinary conditions, carbon atoms cannot spontaneously form a solid diamond structure on this scale. But inside Lucy, the combination of immense pressure, extreme density, and long-term cooling over billions of years allows atoms to arrange themselves into an organized, crystal-like structure. This means that her density is not only a measure of her compactness, but also the key factor enabling her transformation into a diamond. Without such density, Lucy would remain a hot, gaseous remnant rather than the crystallized jewel we observe today. Furthermore, Lucy's density highlights the contrast between the macroscopic and microscopic worlds. While she appears as a relatively small, unassuming point of light in the constellation Centaurus, internally she is composed of matter packed so tightly that the spaces between atomic nuclei are negligible. The physics governing this dense matter is unlike anything we encounter on Earth. It requires not just knowledge of classical physics, but also quantum mechanics and astrophysics to fully understand. Each teaspoon of Lucy embodies the culmination of billions of years of stellar evolution, compression, and cooling. A concentration of matter and history so extreme that it challenges the very way we conceive of matter in the universe. Even the sheer notion of Lucy's density has practical implications for astronomers. By measuring her mass and radius, scientists can calculate the properties of degenerate matter and confirm theoretical models of white dwarf structure. Lucy serves as a living, albeit crystallized, laboratory for extreme physics, allowing astronomers to test predictions about how stars evolve, how matter behaves under extreme pressure, and how quantum mechanics shapes the universe. Her density is not just a number, it is a window into the fundamental forces that govern all matter, providing insights into conditions far beyond what we can replicate on Earth. In summary, Lucy's extreme density is one of her most defining and awe-inspiring characteristics, a moon-sized object with the mass of the sun, capable of making a teaspoon of her weigh several tons. She challenges our imagination and defies our everyday understanding of matter. It is this incredible compactness that sets the stage for her crystallization into a diamond, that allows her to act as a cosmic laboratory, and that connects her to the broader physics of stellar remnants. Lucy, in her density, is both a marvel of the universe and a monument to the extremes that nature can achieve. A silent, compact, and enduring diamond drifting through the galaxy. At the heart of Lucy lies the secret of her extraordinary nature, her carbon-oxygen core. Unlike the Sun, which is primarily hydrogen and helium in its active life, Lucy's core is dominated by heavier elements forged in the nuclear furnace of her progenitor star. Over billions of years, the hydrogen in her center was fused into helium, and later, helium underwent fusion to produce carbon and oxygen, the essential ingredients that eventually gave rise to her diamond-like structure. This core, formed in the final stages of nuclear burning before the star became a white dwarf, is the very essence of Lucy's identity. It is compact, solidifying over time, and holds the material that will eventually crystallize into a massive cosmic diamond. Carbon and oxygen are particularly important because of their unique atomic properties. Carbon, under extreme pressure, has the capacity to form a lattice structure, a repeating three-dimensional arrangement of atoms that gives rise to diamond. Oxygen, while not directly forming diamonds itself, contributes to the stability and composition of the lattice by combining with carbon to form compounds under stellar conditions, allowing the core to maintain structural integrity. This combination of carbon and oxygen in Lucy's interior is not arbitrary. It is a natural consequence of stellar evolution. Stars like her fuse hydrogen into helium and then helium into carbon and oxygen during the late stages of their lives, leaving behind a residue rich in the elements that make up the very diamonds we value on Earth. In Lucy, however, the scale is unimaginable. Billions of trillions of carats of crystallizable carbon and oxygen locked inside a dense spherical remnant of a once luminous star. The carbon-oxygen core is what ultimately differentiates Lucy from other celestial objects. While neutron stars and black holes may contain extreme densities, their compositions are fundamentally different, and they cannot form diamonds. Lucy's core, by contrast, is made of ordinary atoms, albeit packed under extraordinary pressure. The density squeezes the carbon and oxygen nuclei together, creating conditions that are unattainable on Earth. In a sense, Lucy is a natural diamond found on a scale so vast that even imagining it stretches the human mind. It is a reminder that the universe is capable of turning the ordinary into the extraordinary, using the laws of physics and the passage of time to sculpt matter into forms that inspire awe. Lucy's carbon-oxygen core also explains her longevity and stability. While she no longer fuses elements or generates energy through nuclear reactions, the dense core allows her to maintain structural integrity for billions of years. The carbon and oxygen atoms are locked together by both the immense gravity compressing them and the electron degeneracy pressure preventing collapse. These forces ensure that Lucy remains intact even as she cools over cosmic timescales. Her composition is the reason she can eventually crystallize. Without carbon and oxygen, there would be no lattice structure to form, no cosmic diamond to observe. The precise makeup of her interior is a product of billions of years of fusion, collapse, and cooling. A slow, deliberate process that transforms ordinary elements into an extraordinary phenomenon. Interestingly, Lucy's carbon-oxygen core also acts as a kind of record of her life. By studying her composition, astronomers can reconstruct the fusion processes that occurred in the progenitor star. The ratio of carbon to oxygen, for instance, reveals the temperatures and pressures that existed during the star's helium-burning phase. This means that Lucy is not just a diamond drifting through space. She is also a time capsule, preserving the history of a star that lived billions of years ago. Every atom in her core is a fossil from her stellar past, giving scientists a window into nuclear reactions that occurred long before Earth even existed. The distribution of carbon and oxygen within Lucy is not uniform. As the white dwarf cooled over billions of years, heavier elements tended to sink toward the center, while lighter elements floated slightly above. This stratification helped set the stage for crystallization, allowing the interior to solidify first at the center and gradually extend outward. The process is akin to how impurities settle in a molten material, eventually forming a pure crystalline structure. Lucy's core is therefore not only composed of the right elements for diamond formation, but also arranged in a manner that facilitates this transformation over time. In essence, Lucy's core is the foundation of everything that makes her remarkable. Without the carbon-oxygen mixture, there would be no diamond. Without the immense density, there would be no structural integrity. Without the billions of years of cooling, there would be no crystallization. This core embodies the perfect convergence of chemistry, physics, and cosmic timing. A natural alchemy that turns the remnants of a dead star into one of the most extraordinary objects ever observed. It is here, in the very center of Lucy, that the universe demonstrates its ability to create beauty on a scale that is both scientifically fascinating and profoundly poetic. Lucy's carbon-oxygen core is therefore much more than the sum of its parts. It is a testament to stellar evolution, a laboratory for extreme physics, and a precursor to one of the most extraordinary phenomena in the cosmos, a diamond the size of a moon, forged not by human hands, but by the patient, inexorable forces of nature acting over billions of years. The atoms in her core, compressed and cooled, formed the lattice of a diamond whose magnitude dwarfs anything on Earth, and yet despite this enormity, she remains a single object in the vast cosmos, quietly glimmering from 50 light-years away. The most remarkable and awe-inspiring chapter in Lucy's life is her crystallization process, the transformation that turned her from a dense, hot remnant of a star into a colossal diamond floating silently in space. After Lucy became a white dwarf, her core was composed of carbon and oxygen, compressed to extraordinary densities and held together by the invisible hand of electron degeneracy pressure. At this stage, she was incredibly dense, but still extremely hot, with temperatures at the surface reaching around 12,000 Kelvin, many times hotter than the surface of the sun. Over the course of billions of years, however, Lucy's heat slowly radiated into the surrounding cold of space, allowing her interior to gradually cool. This slow, relentless cooling process is the key to understanding how a white dwarf, like Lucy, can eventually form a solid crystalline structure akin to a diamond. Crystallization in Lucy's core is analogous in principle to the formation of diamonds on Earth, though on a scale and under conditions that are almost impossible to imagine. On our planet, diamonds form deep beneath the Earth's crust, where carbon atoms are subjected to extreme pressures and temperatures over millions of years. In Lucy, the pressures are incomparably greater due to her immense density, and the temperatures, while initially extreme, slowly decrease over billions of years. As the core cools, the carbon ions in her core experience a transition from a liquid-like state to a solid crystalline state. This is not a rapid, dramatic event, but a subtle and gradual process that progresses inward to outward over time. The result is that the inner regions solidify first, while the outer layers of the core take even longer to crystallize. It is a phenomenon that astronomers have predicted theoretically for decades, but only recently confirmed through careful observation of white dwarfs like Lucy. The crystallization of Lucy is not just a static event. It affects her evolution in measurable ways. As the carbon and oxygen atoms form a crystalline lattice, latent heat is released. This release of energy slightly slows her cooling, effectively allowing her to shine faintly for longer than she otherwise would. In a sense, crystallization is like a final, subtle heartbeat of the star, a lingering signature of the processes that occurred during her formation. For astronomers, this latent heat provides a clue that helps confirm the internal structure of white dwarfs and the progression of their cooling. In Lucy's case, the crystallization is evidence of a remarkable natural process in which the laws of physics produce an object both solid and dazzling, a diamond on a scale unimaginable in human experience. Lucy's crystallization also highlights the extraordinary timescales over which cosmic events occur. On Earth, geological processes take millions of years, and even that is hard for us to fully comprehend. Lucy's diamond formation occurs over billions of years, a timescale so vast that it surpasses the entirety of human history. The atoms in her core, once formed in the fiery heart of her progenitor star, have slowly arranged themselves into a lattice, creating a structure that is both incredibly strong and perfectly ordered. This slow, steady progression from hot, dense plasma to solid crystalline matter represents one of the most profound examples of natural artistry in the universe, a silent, patient process that transforms stellar remnants into a cosmic gem. Another fascinating aspect of this crystallization is the scale of the diamond that is formed. Lucy's entire core is solidifying simultaneously under extreme pressure, meaning that the diamond lattice extends across thousands of kilometers. It is, quite literally, A single diamond larger than any human could ever hope to create, containing billions of trillions of carats of crystallized carbon. Unlike diamonds on Earth, which are formed in pockets or veins within rock, Lucy's crystallized core is a cohesive, spherical structure, a perfect gem shaped by gravity and time rather than human hands. The sheer magnitude of this diamond defies comparison, highlighting the mind-boggling scales at which nature operates in the cosmos. Lucy's crystallization process also has profound implications for astrophysics. For decades, astronomers theorized that white dwarfs would eventually crystallize as they cooled, but observing this process directly is challenging because it unfolds over billions of years. Lucy's subtle pulsations provided the first clear evidence that crystallization is occurring in real white dwarfs. By analyzing the way her surface vibrates, astronomers were able to infer the internal structure of the star, confirming that her carbon-oxygen core had indeed solidified. This discovery not only confirmed theoretical predictions, but also provided a rare window into processes occurring on scales both vast and extreme, a combination of density, pressure, and cooling that produces something as tangible and visually striking as a diamond in space. In essence, Lucy's crystallization process is a slow, elegant transformation, a convergence of physics, time, and natural beauty. From a dense, glowing core left behind by a dead star, her carbon and oxygen atoms gradually locked into place, forming a lattice structure across thousands of kilometers. Over billions of years, the invisible forces of electron degeneracy pressure, gravity, and thermodynamics collaborated to create a solid diamond larger than any earthly counterpart. Lucy is both a monument to the life cycle of stars and a tangible symbol of cosmic patience and precision. She reminds us that the universe works on scales of time and space that are almost impossible to grasp, producing beauty in forms that transcend our imagination. Through this crystallization, Lucy is no longer just a stellar remnant. She is a diamond star, a glittering testament to the patience of cosmic processes. Every pulsation, every photon escaping her surface carries the story of billions of years of cooling, compression, and atomic organization. It is a story that connects the life and death of a star to the physics of matter itself and transforms what might have been an ordinary white dwarf into one of the universe's most extraordinary natural treasures. Lucy's diamond is both literal and metaphorical, a crystallization of time, matter, and wonder in a single, silent celestial sphere. Lucy is not just remarkable for her composition or her crystallization. Her sheer size and mass elevate her into the realm of cosmic awe. While on Earth, diamonds are measured in carats and prized for their rarity, Lucy defies all conventional scales. Her carbon-oxygen core, crystallized over billions of years, is estimated to contain around 10 billion trillion carats. To put that in perspective, no gemstone on Earth, no diamond, no emerald, no ruby, can even begin to compare. The total value, if it could somehow be quantified in human economic terms, would dwarf every market and treasure combined, reaching numbers so vast that they're almost meaningless in our everyday experience. But more than monetary comparison, the immensity of Lucy helps us grasp the magnitude of cosmic processes and the incredible scales at which stars live and die. Physically, Lucy measures roughly 4,000 kilometers in diameter, comparable to the size of our moon. While that might seem modest compared to the Sun, which spans about 1.39 million kilometers across, the comparison belies her incredible density. She compresses nearly the mass of the Sun, over 330,000 times the mass of Earth, into a sphere no larger than a satellite in lunar orbit. Imagine squeezing the entirety of our Sun, a colossal nuclear furnace, down to the volume of a medium-sized moon, and you begin to comprehend the astonishing density and compactness that define Lucy. Every teaspoon of her material weighs several tons, yet she spans thousands of kilometers, creating a balance between volume, mass, and structure that is almost unfathomable. To help visualize this further, think about familiar objects and scales. The moon itself is the largest natural satellite in our solar system, relative to the planet it orbits, and yet Lucy mirrors that size while carrying far more mass. If Lucy were placed in orbit around Earth, the gravitational forces she would exert would be catastrophic. Her diameter, though similar to the moon, contains within it the full memory of a star's life, compressed into an unimaginably dense crystalline core. Every kilometer, every centimeter of Lucy contains matter forged from nuclear fusion and arranged into a lattice structure, making her not just a massive object, but a highly structured, finely tuned relic of stellar evolution. Her size also emphasizes the contrast between perception and reality in the cosmos. From Earth, Lucy appears as a faint, unremarkable point of light among the stars of Centaurus. Yet in reality, she is a giant, moon-sized diamond-structured sphere, a giant jewel forged by the forces of nuclear fusion and cosmic pressure. This discrepancy between apparent size and actual scale highlights the vast distances involved, 50 light-years away, and reminds us that the universe is full of hidden wonders that cannot be understood merely by their brightness or visibility in the night sky. Lucy's presence is a demonstration that size, mass, and structure can all vary independently, and that even a small point of light can harbor unimaginable magnitude within. The astronomical measurement of Lucy's size is itself a triumph of modern science. By analyzing her pulsations and brightness variations, astronomers can infer her radius and mass with surprising precision. These pulsations act like a cosmic heartbeat, revealing her internal structure in a way analogous to how seismologists study the Earth through earthquakes. By interpreting the frequency and amplitude of these vibrations, scientists confirmed not only that Lucy is crystallized, but also that her overall dimensions match estimates of thousands of kilometers across, solidifying the vision of a cosmic diamond the size of a moon. Even the number of carats assigned to Lucy, 10 billion trillion, is almost impossible to comprehend. A single carat is a tiny unit, 200 milligrams, and yet multiplied by this almost incomprehensible number, it suggests a mass far beyond anything we encounter on Earth. It is a measurement that serves more to inspire wonder than practical calculation, a symbol of the vast scale of matter in the universe. Lucy's size, both in physical dimensions and in carats, embodies the extremity of nature's capacity, showing that stars can die and yet leave behind relics of staggering enormity, beauty, and complexity. Moreover, Lucy's size is intimately connected to her crystallization and density. The larger the core, the more carbon and oxygen atoms are available to lock into a crystalline lattice. Her 4,000-kilometer diameter means that billions of tons of matter are organized into an ordered diamond structure, a feat impossible anywhere else in the known universe. Every kilometer from center to surface contains layers of carbon and oxygen atoms, gradually transitioning from solidified core outward, a structural monument to billions of years of cooling and time. Lucy's size ensures that the diamond lattice is not just microscopic or partial, but a global, planetary-scale crystal, making her a singular marvel, a diamond not just in composition, but in absolute magnitude. In essence, Lucy's scale brings together all the extraordinary aspects we've discussed so far. Density, composition, and crystallization converge to form an object that is simultaneously tangible in its physics and unfathomable in its magnitude. A moon-sized diamond, containing the mass of the sun with trillions upon trillions of carats of crystallized carbon, Lucy is a cosmic object that forces us to reconsider our notions of size, value, and the sheer power of stellar evolution. From Earth, she is a faint glimmer in the constellation Centaurus, but in reality, she is a colossal, dense, glittering jewel. A diamond that spans thousands of kilometers, forged by forces that exceed anything imaginable, silently shining in space. The revelation that Lucy is a crystallized diamond star didn't come from a single photograph or direct observation. It came from the careful study of stellar pulsations, subtle vibrations that ripple through the interior of the white dwarf, carrying the story of her structure and composition. These pulsations are akin to seismic waves on Earth, like the tremors we detect during earthquakes.
By observing how Lucy's surface brightens and dims over time, astronomers were able to infer the conditions deep within her interior, revealing for the first time that her carbon-oxygen core had transitioned from a dense liquid-like state into a solid crystalline lattice. This method of studying stars is known as astroseismology, and it has revolutionized our understanding of white dwarfs, allowing scientists to see inside objects that are completely inaccessible to direct measurement.
White dwarfs like Lucy are not static objects. Even after nuclear fusion has ceased, they continue to vibrate in subtle and predictable ways. These pulsations are caused by small temperature and density variations within the star, which create waves that propagate through the interior. For Lucy, these waves travel through a core that is gradually solidifying. The key insight came from realizing that the frequency and behavior of these pulsations change depending on whether the interior is liquid or solid. In a fully liquid core, vibrations move in a certain pattern. As the material begins to crystallize, the waves behave differently, slowing down or reflecting in ways that reveal the presence of a solid lattice. By monitoring these variations, astronomers could effectively map the internal state of the star, detecting crystallization without ever physically touching or sampling her material. The technique relies on extraordinary precision. Lucy is 50 light-years away, faintly visible as a point of light in the constellation Centaurus. And yet, through careful measurement of the periodic changes in her brightness, scientists detected subtle patterns corresponding to internal vibrations. The pulsations are tiny, changes in luminosity of just a few thousandths of a magnitude, but when analyzed over long periods and across multiple wavelengths, they provide a detailed fingerprint of the interior. By comparing these observations to sophisticated models of white dwarf structure and cooling, researchers concluded that a significant fraction of Lucy's mass, perhaps 90% of her core, had crystallized. This was the first direct evidence confirming decades of theoretical predictions that white dwarfs undergo crystallization as they cool. The discovery is remarkable not only for what it reveals about Lucy, but also for what it demonstrates about human ingenuity in observing the cosmos. No telescope can directly see into the core of a white dwarf, yet through astroseismology, astronomers can infer its structure, much like how geologists study the Earth's interior through seismic waves. Lucy's pulsations act as a natural diagnostic tool, turning her subtle light variations into a window on physics at extreme density and pressure. Each pulse carries encoded information about density, composition, and the degree of crystallization, effectively allowing scientists to perform a kind of remote tomography on a star thousands of trillions of kilometers away. The process of detecting crystallization also confirms key theoretical models of stellar evolution. For decades, astrophysicists predicted that as white dwarfs cool, their carbon-oxygen interiors should gradually form solid crystals. This crystallization is accompanied by latent heat release, a subtle energy output that slightly slows the cooling process. Lucy's pulsations were consistent with these predictions, providing compelling evidence that the theory matched reality. By observing how her vibrations differed from those expected in a purely liquid interior, scientists could quantify how much of her core had solidified and confirm the exact nature of the crystallization. In other words, the patterns of light flickering from Lucy's surface are not random. They are a coded message from the universe, revealing the inner workings of one of its most extraordinary objects. Astroseismology also allowed scientists to estimate how far along Lucy is in the crystallization process. Models indicate that her core has been solidifying over billions of years, with the process likely continuing slowly toward the outer layers. This means that Lucy's diamond is still growing in a sense, as additional layers of her interior gradually settle into the crystalline lattice. Observing her pulsations provides a live snapshot of an ongoing process that spans cosmic timescales, letting astronomers witness the patient, precise work of the universe
as it builds something that would be literally impossible to replicate on Earth. What makes Lucy's crystallization discovery even more profound is that it bridges theory and observation. The notion that white dwarfs could crystallize was proposed in the 1960s and 1970s, based on theoretical physics and models of dense matter. Yet, until Lucy's pulsations were carefully analyzed, this concept remained speculative. Through a combination of long-term observations, precise photometry, and comparison with models, scientists finally confirmed that white dwarfs are capable of forming solid, diamond-like cores. A realization that not only transformed our understanding of these stellar remnants, but also gave rise to the poetic notion of a diamond star drifting through space. In summary, the evidence for Lucy's crystallization comes from the study of her stellar pulsations, tiny rhythmic variations in her brightness that encode information about her interior. Through astroseismology, astronomers have been able to detect the transition from a liquid-like core to a solid crystalline structure, revealing that the carbon and oxygen at her heart have locked into a diamond lattice. This discovery is a triumph of modern astrophysics, showing that even distant, faint stars can communicate their internal secrets through subtle vibrations. Lucy, in pulsating softly across space, not only tells us her story, but also validates decades of theoretical predictions, proving that she is indeed the largest diamond in the universe, a silent, solid jewel formed over billions of years. Lucy's discovery and the confirmation of her crystallized core are more than just a fascinating cosmic anecdote, but represent a major milestone in stellar physics and our understanding of the life cycle of stars. For decades, astrophysicists had predicted that white dwarfs, the remnants of stars like our Sun, would not simply cool quietly into invisibility, but would undergo a slow crystallization process as their dense carbon-oxygen cores solidified. This hypothesis was based on complex models of quantum mechanics, stellar structure, and thermodynamics, but until Lucy's pulsations were carefully studied, it had never been directly confirmed. The observation of her crystallized interior provided the first tangible proof that these models were correct, giving astronomers not only confidence in their theories, but also a real example of physics operating at cosmic extremes.
The significance of Lucy's confirmation is multifaceted. White dwarfs are essentially the endpoint for the vast majority of stars in the universe, including stars similar to our Sun. Understanding how they evolve and cool is therefore critical for constructing accurate models of stellar populations and galactic evolution. The cooling rate of white dwarfs informs astronomers about the age of star clusters, the formation history of galaxies, and even the timeline of the universe itself. Lucy's crystallization showed that the cooling process is slightly delayed by the release of latent heat during crystallization, an effect that theoretical models had predicted but which had never been observed directly. By quantifying this process, Lucy allowed astrophysicists to refine their calculations of stellar ages with unprecedented precision. Before Lucy's discovery, white dwarfs were often treated as relatively simple objects, dense, hot spheres of degenerate matter gradually fading into obscurity. But Lucy revealed that these remnants are dynamic and complex, undergoing structural changes over billions of years. The crystallization of her carbon-oxygen core demonstrates that white dwarfs are not just passive remnants, but active participants in the physics of matter under extreme conditions. This has implications far beyond Lucy herself. Understanding crystallization helps scientists probe the behavior of matter at incredibly high pressures and densities, providing a natural laboratory for physics that cannot be replicated on Earth. Electron degeneracy, lattice formation, and latent heat release are all phenomena that are extremely difficult to study in terrestrial laboratories, but Lucy makes them observable in a cosmic context. Lucy also confirmed an important prediction about the final stages of stellar evolution. Theoretical models have suggested that as white dwarfs cool, their cores gradually crystallize from the inside out. Lucy's pulsations provided direct evidence of this inward to outward solidification,
showing that the process takes billions of years and that the solid core can eventually encompass nearly the entire star. This confirmation not only validates decades of theoretical work, but also opens the door to studying other white dwarfs in a similar manner. Each pulsating white dwarf can now be examined as a potential crystallization candidate, allowing astronomers to build a larger understanding of the population and diversity of these objects in the galaxy. The broader importance of Lucy also lies in what she tells us about the future of our own sun. Stars like the sun will one day exhaust their nuclear fuel, shed their outer layers, and leave behind white dwarfs. Lucy offers a preview of that eventual outcome. Her crystallization shows the endpoint of solar-like stellar evolution, allowing scientists to model the long-term fate of our solar system and predict how matter behaves at extreme densities over billions of years. In this way, Lucy is not only a diamond floating in Centaurus, she is a cosmic time machine, a guide to understanding processes that will occur in our own neighborhood far into the future. From a scientific perspective, Lucy also serves as the benchmark for astroseismology. By analyzing the minute variations in her brightness, astronomers can measure her internal structure, cooling rate, and crystallization progress. These methods have now become standard tools for studying other white dwarfs, turning Lucy into a prototype for understanding stellar remnants across the galaxy. Without her, the theory of white dwarf crystallization might have remained speculative for decades longer, but her presence and the careful study of her pulsations transformed theory into confirmed observation.
Finally, Lucy matters because she is an extraordinary demonstration of nature's capacity to combine extremes. Extreme density, extreme pressure, and extreme timescales come together to form something both scientifically significant and visually poetic. She bridges the gap between abstract physics and tangible reality, showing that the universe's laws operate with precision even in objects unimaginably far away. By studying Lucy, scientists have been able to validate models of stellar cooling, test theories of matter under extreme conditions, and gain insight into the ultimate fate of stars like our sun. Her crystallization is more than a curiosity. It is a cornerstone of modern astrophysics, a rare opportunity to see the interplay of physics on a scale that combines beauty, magnitude, and fundamental science. In essence, Lucy matters because she confirms the predictions of stellar evolution, provides a laboratory for extreme physics, and acts as a window into the distant future of stars, including our sun. She transforms the abstract into the observable, the theoretical into the tangible, and in doing so, she secures her place not just as a diamond in the sky, but as a milestone in our understanding of the cosmos. Her presence validates decades of work, demonstrates the power of observation, and reminds us that even in death, stars can illuminate the universe, literally and metaphorically, in ways that continue to expand human knowledge and wonder. Lucy is not just a distant marvel. She also serves as a glimpse into the distant future of our own sun, offering a tangible preview of what will eventually happen to the star that lights our world. Right now, the sun is a relatively stable main sequence star, burning hydrogen into helium in its core and providing the steady energy that makes life on Earth possible. But like all stars of similar mass, the sun has a finite lifespan. In roughly 5 billion years, it will exhaust its hydrogen fuel at the core, and the delicate balance that keeps it stable will begin to collapse. This sets off a dramatic sequence of transformations that will ultimately produce a white dwarf remarkably similar to Lucy. As the sun's core runs out of hydrogen, it will expand dramatically into a red giant, swelling to possibly engulf the inner planets, including Mercury, Venus, and perhaps even Earth. This phase will last for hundreds of millions of years, a brief but tumultuous chapter in the sun's life. During this period, the sun will begin fusing helium into heavier elements, such as carbon and oxygen. Eventually, the outer layers will be ejected into space, forming a planetary nebula,
a glowing shell of gas that will carry material enriched with carbon, oxygen, and other elements into the galaxy. What remains at the center of this process is the Sun's dense carbon-oxygen core, compressed by gravity, similar in structure to Lucy before her crystallization begins. Over the subsequent billions of years, this remnant will slowly cool and contract, transitioning into a white dwarf. Unlike Lucy, the Sun's white dwarf stage will begin as a hot, glowing object, radiating away residual heat but no longer generating energy through fusion. Gradually, as the Sun loses heat, the carbon and oxygen in its core will start to arrange themselves into a crystalline lattice, forming a diamond-like structure analogous to Lucy's. In other words, the Sun itself will one day become a diamond star, albeit on a slightly smaller scale, quietly shining in the vast darkness of space, invisible to the naked eye, but carrying the same frozen story of stellar evolution that Lucy now demonstrates.
Lucy offers more than just a poetic mirror for the Sun's future. She provides critical scientific insight into what that transformation will look like. By observing her crystallized core, astronomers can study the cooling rates, internal structures, and crystallization processes that will apply to the Sun billions of years from now. This is invaluable because we cannot accelerate time to witness our Sun's distant fate. Lucy acts as a time machine, showing us the endpoint of solar evolution in the present, giving clues about the timescales and processes involved, and allowing us to make precise predictions about the structural and chemical evolution of our own star. The connection between Lucy and the Sun also emphasizes the universality of stellar processes. Stars, regardless of their location in the galaxy, follow predictable life cycles based on their initial mass. Lucy's story demonstrates that the carbon-oxygen crystallization observed in a white dwarf 50 light-years away will also occur in our Sun. In this way, Lucy becomes a cosmic benchmark, a proof of concept for theories about white dwarf formation, cooling, and crystallization. By studying her, we gain a preview of the ultimate fate of our solar system and can better understand the future of stellar remnants throughout the galaxy. Furthermore, this connection invites a reflection on the continuity and recycling inherent in cosmic evolution. Just as Lucy preserves the remnants of a star that lived billions of years ago, the Sun's future white dwarf stage will be a legacy of the processes occurring today. The Sun's outer layers, once expelled, will enrich the galaxy with carbon, oxygen, and other elements that may one day form new stars and planets, continuing the endless cycle of creation, death, and rebirth. Lucy, in her crystallized form, is both an endpoint and a guidepost, showing us that even as stars die, they leave behind structures that are both scientifically valuable and visually awe-inspiring. In essence, the story of Lucy provides a mirror for the Sun's destiny. 5 billion years from now, the Sun will exhaust its nuclear fuel, expand into a red giant, shed its outer layers, and leave behind a dense carbon-oxygen core. Over billions more years, that core will crystallize, becoming a solid diamond-like structure like Lucy, silently floating in space, carrying the memory of the Sun's life and the forces that shaped it. Lucy is therefore not just a distant curiosity, she is a preview, a lesson, and a cosmic forecast of what awaits our own star, bridging the immense scales of time and space that govern stellar evolution. Lucy, as fascinating as she is in appearance and composition, is known in the astronomical catalog by a more technical designation, BPM3 7093. While Lucy evokes poetic imagery, a nod to the Beatles song Lucy in the Sky with Diamonds, the formal name originates from scientific classification systems that astronomers use to catalog stars, particularly variable stars, those whose brightness changes over time. The acronym BPM comes from the Bruce Proper Motion Survey, which was conducted at the Harvard Smithsonian Center for Astrophysics. The survey aimed to identify stars with measurable proper motion, that is, stars whose positions change noticeably over time against the backdrop of more distant celestial objects. Each star identified in this catalog is assigned a unique number, in Lucy's case 37093, to distinguish her from thousands of other stars detected in the survey. The use of BPM 37093 as a designation reflects the rigorous structure of astronomical cataloging. While poetic names like Lucy capture public imagination, professional astronomers rely on systematic identifiers to ensure clarity, especially when studying stars that share similar properties. The BPM prefix helps scientists immediately recognize the survey of origin, while the numeric suffix identifies the star's sequence within that survey. This allows astronomers across the world to communicate precisely about Lucy without ambiguity. When they refer to BPM 37093 in a paper or observation log, every scientist knows exactly which star is under discussion, which is crucial when analyzing phenomena like pulsations, crystallization, and white dwarf cooling, processes that require extremely accurate and reproducible measurements. Interestingly, Lucy's dual identity as both BPM 37093 and Lucy highlights the interplay between science and human culture. The technical designation represents her place in a structured observational universe, a catalog point of data governed by the laws of physics. The nickname, however, evokes wonder and imagination, making her story accessible beyond the scientific community. Astronomers chose Lucy not randomly, but deliberately, referencing the Beatles song that famously celebrates diamonds in the sky. The name links the object's literal composition, a crystallized diamond-like core, with a familiar cultural reference, making the marvel of a diamond star relatable and memorable for the public while preserving scientific rigor with BPM 37093. The cataloging of Lucy under BPM 37093 also reflects the broader history of variable star research. Variable stars have been studied for centuries, initially through naked-eye observations and later with sophisticated telescopes. These stars can vary in brightness due to pulsations, eclipses, or other intrinsic or extrinsic factors. Lucy's pulsations, which ultimately revealed her crystallized core, were detectable precisely because she had been identified and cataloged in surveys like the Harbor-Smithsonian BPM survey. Without such catalogs, astronomers might never have targeted her for detailed study, and the discovery of the first crystallized white dwarf would have been delayed. In this sense, BPM 37093 is not just a label, it is a gateway to discovery, connecting historical methods of star cataloging to cutting-edge astrophysics. The origin of Lucy's formal name underscores the meticulous nature of astronomical observation. Each step, from measuring proper motion to cataloging brightness variations, contributes to a system that allows stars to be studied scientifically across generations and continents. BPM 37093 represents Lucy's identity within that system, a testament to human curiosity, precision, and a persistent effort to map the heavens. Yet, behind the numbers lies the poetic reality of her existence, a crystallized diamond larger than the moon, floating silently 50 light-years away. This duality, a cold, technical label paired with a warm, imaginative nickname, perfectly encapsulates the nature of Lucy herself, both a rigorously understood astrophysical object and a source of wonder that sparks the imagination. Moreover, understanding the origin of BPM 37093 emphasizes the importance of scientific catalogs in modern astronomy. Every measurement, observation, and discovery builds upon a foundation of carefully logged data. Surveys like the Harvard-Smithsonian BPM survey are designed not only to identify stars, but to create a lasting reference framework for future research. Lucy's pulsations, crystallization, and extreme properties could only be contextualized because she was cataloged, named, and observed systematically. The technical designation ensures that subsequent studies of her properties, whether her temperature, mass, radius, or pulsation frequencies, are reproducible and accurately linked to a specific object in the sky. In essence, Lucy's formal name, BPM 37093, connects her to a long tradition of careful astronomical study, while her nickname immortalizes her as a cosmic marvel. The combination of catalog precision and cultural resonance make her accessible to both scientists and the public, emphasizing that astronomy is a discipline that balances exactitude with inspiration.
BPM 37093 is the star we study with telescopes, measure with instruments, and model with physics, while Lucy is the star that captures the imagination, the diamond in the sky whose existence tells a story of stellar evolution, crystallization, and cosmic beauty. The name, in its dual form, perfectly mirrors her essence, simultaneously scientific, precise, and breathtakingly extraordinary. Lucy, though a silent and seemingly cold jewel drifting through the cosmos, is far from frozen in the sense of temperature. Her surface radiates at an astonishing 12,000 Kelvin, which is over twice as hot as the sun's surface, which sits at around 5,778 Kelvin. To put that in perspective, her surface is glowing with an intense bluish-white light, hotter than any incandescent filament we could produce on Earth. Despite her incredible density and crystallized core, Lucy is still radiating the residual heat left over from her days as an active star. Unlike living stars, she no longer generates energy through nuclear fusion, but the thermal energy trapped within her dense core continues to escape slowly into the void, allowing her to shine for billions of years as a cooling, crystallized remnant.
The high surface temperature of Lucy also plays a crucial role in our ability to study her. Her intense glow allows telescopes to detect her despite being 50 light-years away, and her pulsations, the subtle fluctuations in brightness caused by internal vibrations, are easier to observe because of this energy emission. These pulsations carry the information needed to understand her crystallized interior and confirm the predictions of stellar evolution. Interestingly, while 12,000 Kelvin is searingly hot and the lifespan of a white dwarf, this is already a stage of advanced cooling. White dwarfs begin their lives at temperatures exceeding 100,000 Kelvin, and over billions of years, they gradually radiate their energy away. Lucy, at 12,000 K, is a mature white dwarf, well along the path toward eventual invisibility as a black dwarf, a state theorized to occur when a white dwarf has cooled completely, trillions of years into the future. Lucy's age is equally staggering, estimated at around 11 billion years, making her older than our solar system, which is about 4.6 billion years old. This age situates her among some of the oldest stellar remnants we can observe in our galactic neighborhood. To think that Lucy formed so early in the history of the Milky Way is mind-boggling. She has witnessed the galaxy's evolution from nearly its formative stages, survived countless cosmic events, and now drifts silently through space, a relic of an ancient stellar past. Her age also provides context for her crystallization. Such a slow process requires immense timescales, and Lucy's 11 billion-year lifespan explains how her core could have gradually transformed into a solid, diamond-like lattice. The combination of her temperature and age tells a story about the life cycle of stars. Lucy's temperature indicates that she is still shedding the heat from her earlier life as an active star, and her age confirms that billions of years of slow cooling have allowed her carbon-oxygen core to crystallize. This carrying of intense heat and extreme longevity makes her an extraordinary laboratory for astrophysics. Scientists can model how white dwarfs cool over time, test theories of heat transfer in degenerate matter, and estimate how long it will take for other stars, including the Sun, to reach similar stages. Lucy, glowing at 12,000 K, yet already ancient, is living proof of the delicate interplay between thermal energy, density, and time in stellar remnants. Lucy's temperature also has implications for her visibility and study. Despite her immense distance, she shines with enough intensity in visible and ultraviolet light that astronomers can measure her pulsations, surface temperature, and cooling rate with high precision. Her age, combined with the degree of crystallization, allows scientists to calibrate models of white dwarf evolution across billions of years. By comparing Lucy to younger or hotter white dwarfs, researchers can trace a timeline of cooling and structural transformation, effectively using her as a cosmic chronometer, a way to measure the passage of time on scales far beyond human comprehension.
Moreover, Lucy's age emphasizes the patience of cosmic processes. 11 billion years is almost 3 times the current age of Earth. In that time, the universe has expanded, galaxies have collided, stars have been born and died,
And yet Lucy persists, a dense, crystalline monument to the life of her progenitor star. Her surface temperature may gradually decline over the next several billion years, but her core will retain its crystalline structure, a frozen record of a star that has long since ceased nuclear fusion. In this sense, Lucy embodies both motion and stillness, radiating faint light while her interior remains solid and eternal, a paradox that captures the very essence of stellar remnants. In short, Lucy's surface temperature of 12,000 Kelvin and age of 11 billion years provide a window into her past and future. They reveal a star that is mature, cooled yet glowing, ancient yet still interacting with the universe around her through light and pulsations. They allow astronomers to understand the timing and physics behind white dwarf crystallization, link her properties to the life cycle of stars like our Sun, and illustrate the unimaginable scales of both heat and time that govern cosmic evolution. Lucy is therefore not just a diamond star in composition, she is a chronometer of the cosmos, telling a story that spans nearly the entire history of the Milky Way, a story written in light, heat, and crystallized carbon. Approaching Lucy, the diamond star in our imagination, is like stepping into a world that defies ordinary perception, a realm where physics meets artistry on a cosmic scale. From a distance, Lucy appears as a faint, bluish-white point of light in the constellation Centaurus, barely distinguishable to the naked eye. But up close, a purely hypothetical perspective, as traveling 50 light-years remains far beyond our current capabilities, her surface and interior would present a spectacle both alien and familiar. Imagine the polished brilliance of a diamond, magnified thousands of times and then expanded to a sphere 4,000 kilometers across, dense enough that even the tiniest fragments would weigh more than a skyscraper. Her surface would glimmer with a luminous, almost ethereal bluish-white radiance, the energy of 12,000 Kelvin light escaping from her crystallized core, casting a ghostly glow that seems to shimmer through the very lattice of carbon and oxygen atoms beneath. If you could somehow hover near her surface, the texture would be unimaginable. Unlike a traditional gemstone, which is smooth and reflective because of its cut and polish, Lucy's diamond is a natural planetary scale lattice. The carbon and oxygen atoms are arranged in perfect crystal structures, but on scales that far exceed human comprehension. It's as if someone had taken a flawless diamond, magnified it to the size of a small moon, and then compressed it so intensely that a teaspoon of material would weigh tons. You might visualize the surface as subtly rippling with pulsations, the faint vibrations that have revealed her crystallized core to astronomers. These tremors would be imperceptible to human senses, but in principle, they carry the heartbeat of the star, a rhythmic signature of energy moving through her rigid crystalline lattice. The color of Lucy would be striking. While diamonds on Earth are typically clear, some with tints of blue or yellow due to impurities, Lucy's massive crystal is pure carbon and oxygen, glowing with the energy of a hot white dwarf. The combination of extreme heat and crystalline perfection would give her a radiant bluish-white hue, brighter than the brightest gemstones but diffused across a vast spherical surface. If you could see her from a fraction of a lunar distance, she might appear as a perfectly smooth, glowing orb, reflecting light with an inner brilliance that seems to emanate from within rather than bouncing off the surface. Unlike a man-made diamond, which depends on an external light source to sparkle, Lucy shines from her own residual thermal energy, making her a self-illuminating gem in the blackness of space. Textures at smaller scales would defy imagination. On Earth, diamond crystals have flat facets and sharp edges, but Lucy's lattice is continuous and cohesive on a planetary scale, without cracks or interruptions. Every atom in the core is locked into place, forming a structure that extends from the center to the outer layers. The surface itself is likely irregular at microscopic scales due to residual energy gradients and temperature differences, creating subtle, almost imperceptible patterns across her sphere. Light escaping from Lucy would refract slightly as it passes through the crystallized lattice,
producing faint spectral distortions, like a jewel viewed through hundreds of layers of glass, magnified and warped across thousands of kilometers. This would create an effect unlike any gemstone on Earth, a deep, luminous shimmer that carries with it the story of billions of years of cooling and crystallization. The contrast between Lucy's interior and exterior would be remarkable. The core is solid and unyielding, a giant lattice of carbon and oxygen, while the outer layers, though also crystallized, might still contain trace heat or slightly less dense matter. Imagine the transition from liquid to solid in a lava flow, but on a planetary scale, and compressed by gravity to unimaginable densities. This gives the star a kind of layered radiance, a glowing heart of crystallized material gradually merging with the slightly cooler outer regions, producing a gentle gradient of light intensity across her spherical body. Her surface pulsations, the subtle vibrations that astronomers detect from Earth, would create a delicate, almost imperceptible shimmering effect, a living, breathing aspect of a star that is technically dead in terms of fusion, but still active in its own crystalline rhythm. One way to picture Lucy is to compare her to a diamond the size of a moon floating in a dark ocean of space. The ocean, in this analogy, is the void of interstellar space, a black backdrop that makes her glow stand out even more vividly. Unlike a terrestrial diamond embedded in jewelry, Lucy is fully exposed, radiating her internal heat outward, unaffected by surrounding structures. Her size, density, and perfection of lattice would make her appear almost unreal to any observer, a jewel shaped not by human hands, but by the patient, relentless forces of gravity, nuclear fusion, and billions of years of cooling and crystallization. She is both a natural sculpture and a monument to cosmic precision.
In addition, Lucy's pulsations would create dynamic visual effects if one could perceive them. As internal waves ripple through the crystallized core, the light emission might fluctuate slightly, giving the appearance of a living gemstone, subtly shimmering in patterns too intricate and vast to be noticed from Earth. The vibrations act as a heartbeat for the star, revealing not just her structure, but her history, as every oscillation is a record of her thermal evolution and crystallization. Unlike any gemstone we know, Lucy is alive in a physical sense. Her interior is still subtly active, and her brilliance is a product of the energy slowly radiating from her dense core. In essence, a close-up view of Lucy is a fusion of extreme science and poetic imagination. She would look like a massive, glowing diamond, blue-white in color, with a surface subtly alive with pulsations, radiating heat from a crystalline lattice spanning thousands of kilometers. Her brilliance comes not from reflections, as with earthly gems, but from the energy trapped in her dense interior. She is at once alien and familiar, a tangible representation of stellar evolution and the diamond of unparalleled scale, formed naturally through cosmic forces over billions of years. Lucy is the universe's ultimate gemstone, both a scientific marvel and the symbol of beauty and precision in the cosmos. Studying Lucy, a diamond star 50 light-years away, requires a remarkable combination of precision, ingenuity, and indirect observation, because no telescope can physically reach her or directly sample her interior. Astronomers rely on several key methods to gather information about distant stars like Lucy, turning faint light into a wealth of data about structure, composition, temperature, and evolution. These techniques, combining physics, mathematics, and observational astronomy, allow scientists to reconstruct the full story of her existence, from her surface temperature to the crystallization of her carbon-oxygen core. Among the most critical tools are spectroscopy, pulsation timing, and theoretical modeling, each offering a unique window into the star's characteristics. Spectroscopy is one of the primary methods astronomers use to understand stars at a distance. By splitting Lucy's light into its component wavelengths, scientists can analyze her spectrum to determine both her chemical composition and temperature. Every element absorbs and emits light at specific wavelengths, producing a unique fingerprint that reveals the elements present in the star. For Lucy, spectroscopy confirms the dominance of carbon and oxygen in her core,
and can also detect traces of other elements in her outer layers. Additionally, the spectrum helps determine her surface temperature, which in Lucy's case is about 12,000 Kelvin. Spectroscopic measurements also provide information about the star's motion relative to Earth through the Doppler shift of spectral lines, giving clues about her orbit, velocity, and interactions with the surrounding galaxy. In essence, spectroscopy converts light into a precise map of composition and energy, allowing scientists to infer properties that would otherwise be invisible. While spectroscopy reveals the ingredients of Lucy, pulsation timing unlocks her internal structure. Lucy is a pulsating white dwarf, meaning that her brightness oscillates subtly due to vibrations that propagate through her interior. These oscillations are incredibly small, changes in brightness of just a few thousandths of a magnitude. But by measuring them over time, astronomers can determine the internal density, crystallization fraction, and structural composition of the star. This technique, known as astroseismology, is analogous to studying the Earth's interior with seismic waves generated by earthquakes. Just as geologists can infer the layers of the planet from wave behavior, astronomers use Lucy's pulsations to map her core, detect the presence of a crystallized lattice, and measure the size and density of various layers. Each pulse acts as a natural probe, carrying encoded information about temperature gradients, elemental distribution, and crystallization progress, revealing details impossible to observe through direct imaging. The third critical approach is theoretical modeling, which ties together observations from spectroscopy and pulsation timing into a coherent physical understanding. Scientists build sophisticated computer models of white dwarfs that simulate their formation, cooling, and crystallization over billions of years. These models incorporate the laws of quantum mechanics, thermodynamics, and nuclear physics to predict how stars like Lucy evolve from their main sequence phases to white dwarfs and eventually to crystallized diamond cores. By comparing the models with observed pulsation frequencies, brightness, and spectral data, astronomers can test and refine their understanding of stellar evolution. In Lucy's case, modeling confirmed that her pulsations were consistent with a largely crystallized carbon-oxygen core, and allowed researchers to estimate the fraction of her mass that had solidified, the rate at which she is cooling, and her approximate age of 11 billion years. An essential part of these methods is cross-validation. No single technique gives a complete picture. Spectroscopy tells us composition and surface temperature, but cannot reveal interior crystallization. Pulsation timing reveals the internal structure, but relies on precise models to interpret the vibrations correctly. Theoretical models predict behavior over time, but they need observational data for confirmation. By combining these methods, astronomers achieve a remarkably detailed understanding of Lucy, despite her distance and the impossibility of direct contact. This triangulation of observation and theory demonstrates the power of modern astrophysics to study objects across light years with incredible precision. Other subtle techniques also contribute to our knowledge of Lucy. For example, measuring the cooling rate over long periods allows scientists to estimate how quickly heat escapes from Lucy's core, providing additional insight into crystallization and density. Similarly, high-resolution imaging can refine distance estimates and help confirm luminosity, while photometric surveys track pulsation patterns over extended periods. Even gravitational effects on nearby stars can provide minor but useful constraints on her mass and motion. Together, these methods create a comprehensive profile of Lucy, transforming her from a faint point of light into a fully characterized astrophysical object. Ultimately, these astronomy methods reveal the elegance of studying the cosmos indirectly. Lucy cannot be touched or visited, yet through the combination of light analysis, pulsation detection, and computer modeling, we know more about her than many geological features on Earth. We can measure her mass, radius, temperature, age, and internal crystalline structure, even from 50 light-years away. In doing so, astronomers have turned abstract physics into tangible knowledge, demonstrating that the universe communicates its secrets through light, vibration, and time. And that with ingenuity, humans can decipher those messages even across the vast reaches of space. Lucy is both a test of these techniques and a triumph of their application, a diamond star whose existence is confirmed not by proximity, but by the careful study of its subtle signals, revealing the interplay of matter, energy, and time on scales almost impossible to imagine. Speculating about mining Lucy is a fascinating exercise in both imagination and absurdity, because it combines the allure of unimaginable wealth with the stark realities of physics and space travel. Imagine, for a moment, that we somehow had the technology to journey 50 light-years away to the Centaurus constellation, reach Lucy's surface, and begin the extraction of her crystallized carbon-oxygen core. Even if such a journey were physically feasible, which it is not with our current understanding of space travel, the scale and density of Lucy make mining her an impossible challenge. A teaspoon of her material weighs several tons, meaning that even a small chunk removed from her surface would require forces and containment technology beyond our wildest engineering capabilities. Yet, as a thought experiment, imagining the sheer value of Lucy is irresistible. Let's talk numbers. Lucy's core is estimated to contain around 10 billion trillion carats of crystallized carbon, a quantity so vast it defies ordinary comprehension. Even if we try to assign earthly monetary value to that, every carat of diamond mined on our planet pales in comparison. By simple calculation, the combined worth of Lucy's diamond material would far exceed all the economic activity on Earth over millennia, essentially dwarfing the entire global economy many times over. This is not just a financial exaggeration. It's literally a reflection of the sheer quantity and density of crystalline carbon packed into her sphere. Hypothetically, humanity would instantly become unimaginably wealthy, though of course, the problem is that the value is entirely conceptual because there is no feasible way to extract or transport it. The challenges go far beyond economics. Lucy's gravity is extreme and her density is immense. A mining operation would need to contend with forces that would crush any conventional equipment, not to mention the blistering surface temperatures of 12,000 Kelvin. Any robotic or human mission attempting to interact with her would vaporize instantly without fantastical, almost magical technology. Moreover, extracting material from her interior would destabilize the very structure of the star, potentially unleashing catastrophic energy releases. Unlike mining a terrestrial diamond where gemstones are embedded in rock and handled delicately, Lucy is a planetary-scale crystal under immense pressure, and any attempt to extract even a gram would require containing forces equivalent to entire mountains compressed into infinitesimal volumes. Even if we ignore the technological impossibilities, the thought of Lucy's sheer volume of diamonds is mind-boggling. To put it into perspective, a single carat weighs 0.2 grams, and Lucy has around 10 billion trillion carats. That's approximately 2 times 10 to the 30 kilograms of diamond, roughly comparable to the mass of the sun. No conceivable transport or storage system could handle this. Any attempt to bring portions of Lucy back to Earth would not just be logistically impossible, it would literally alter our planet's gravity and orbital dynamics if even a fraction of that mass were relocated. The absurdity of the scale is what makes the exercise fun. We are imagining wealth and abundance far beyond human experience, yet it also underscores the immense size and density of this cosmic object. It's also worth considering the hypothetical economic implications. If Lucy's diamond material were somehow brought to Earth, its abundance would collapse the very concept of value. Diamonds are precious precisely because they are rare. Flooding the market with trillions of carats would make them essentially worthless by conventional standards. Ironically, in this imaginary scenario, the richest diamond star in the universe might simultaneously destroy the market for diamonds on Earth, showing how value is not just about quantity, but scarcity and context. Lucy, in this sense, is both a cosmic treasure and a cautionary tale about the relativity of wealth when measured on astronomical scales. Despite the impossibility of mining her, Lucy sparks the imagination in other ways. She reminds us that the universe produces forms of matter that far exceed anything we can manufacture. Humanity has mastered small diamonds in laboratories and mines, but Lucy is a diamond larger than the moon, formed naturally and glowing from residual heat, a monument to cosmic patience and precision. The playful thought of mining her underscores just how extreme the universe can be, a reminder that our earthly definitions of wealth, luxury, and value are insignificant compared to the scale of astrophysical phenomena. Finally, Lucy as a mineable diamond offers an interesting philosophical reflection. Even if we could harvest her, would we want to? The beauty of Lucy lies not in her potential value, but in her existence as a cosmic relic. A silent monument to the life cycle of stars. She is priceless not because she can be monetized, but because she embodies the forces of nature, time, and physics on a scale far beyond human imagination. In the end, Lucy teaches us that some treasures are meant to be admired, studied, and marveled at, not extracted. Her impossibility is part of her allure, the ultimate diamond that cannot be owned, only observed, studied, and appreciated across light years of distance. In summary, imagining mining Lucy is a whimsical and awe-inspiring thought experiment. She represents value beyond measure, with carats and mass that surpass all earthly economies. Yet, the challenges of density, gravity, and distance make it entirely impossible. The exercise highlights both the extremes of the universe and the limits of human technology, while reminding us that Lucy's true worth lies not in what could be extracted, but in her existence as a crystallized relic of stellar evolution, a cosmic diamond we can marvel at from afar. Lucy, dazzling as she is today, is not frozen in time. Her story continues over billions of years into the future, a slow, inevitable progression toward a state of ultimate silence and darkness. Although she currently glows at a searing 12,000 Kelvin, emitting a bluish-white light visible across 50 light-years, she is already well into the long cooling process typical of white dwarfs. Unlike active stars, she no longer generates energy through nuclear fusion. Instead, she radiates the residual thermal energy stored within her dense carbon-oxygen core. Over the next billions of years, this energy will gradually dissipate into the cold expanse of interstellar space, causing Lucy to dim and cool progressively, transitioning from a luminous white dwarf into a state almost completely imperceptible. The endpoint of this transformation is what astronomers call a black dwarf, a stellar remnant that has cooled so thoroughly that it emits no detectable light or heat. In this stage, Lucy will still retain her incredible density and her crystallized carbon-oxygen lattice. Effectively, she will become a frozen, invisible diamond floating silently in space. From a human perspective, this is almost impossible to grasp. Imagine a moon-sized diamond, composed of material denser than anything we can produce, that has cooled to near absolute zero and no longer shines, drifting silently through the galaxy. The black dwarf is a ghostly relic, a monument to the star that once burned fiercely, now existing as a timeless structure of matter, unchanging yet completely hidden. The timeline for this transformation is staggeringly long. White dwarfs like Lucy cool very slowly because of their immense density and the insulating properties of their crystallized interiors. It is estimated that the universe is not yet old enough for any white dwarf to have become a black dwarf. Lucy herself, at about 11 billion years old, is still glowing brightly. But over the course of tens or hundreds of billions of years, timescales far exceeding the current age of the universe, she will radiate away the last traces of residual heat. When that happens, Lucy's glow will fade entirely, and she will join the ranks of black dwarfs, objects that exist in space as cold, dense, solid remnants of stellar evolution, invisible to even the most powerful telescopes of today.
The existence of black dwarfs is largely theoretical because the universe is not yet old enough for any to have fully formed. Lucy offers a glimpse into the far future of stellar remnants, showing us what awaits stars like the Sun long after the universe has expanded, cooled, and evolved. In that distant era, she will become a silent witness to the galaxy's history, carrying the memory of her fiery past within a perfectly crystallized, solid structure. Her diamond-like interior will endure even when all radiation has ceased, a permanent artifact of the forces that created and shaped her, frozen in time, but no longer interacting visibly with her surroundings. Despite becoming invisible, Lucy's influence will persist in subtle ways. Her immense gravity will continue to shape the orbits of nearby objects, her mass contributing to the gravitational architecture of the Milky Way. In a sense, she will remain an anchor of matter in space, a hidden presence that, though imperceptible to the eye, still exists as part of the galaxy's mass energy distribution. Her crystallized core, a product of billions of years of cooling and solidification, will serve as a testament to the inevitability of stellar evolution and the durability of matter under extreme conditions. Even as a black dwarf, Lucy embodies the universe's ability to create structures that persist across incomprehensible timescales. This transformation also offers a poetic reflection on the nature of cosmic beauty. Today, Lucy is celebrated for its visible brilliance, its diamond-like structure illuminated by residual heat. Tomorrow, billions or trillions of years hence, she will achieve a different kind of magnificence, a silent, invisible diamond, a monument to the slow but inexorable passage of time. Her journey from luminous white dwarf to cold black dwarf exemplifies the full arc of stellar life: birth, fusion, death, crystallization, and ultimate disappearance from visible view. Yet even in invisibility, the physical structure of Lucy remains, a reminder that stars leave behind legacies not just of light, but of matter arranged in ways that endure far beyond their lifetimes. The future of Lucy underscores the grand scales of cosmic time, where processes occur over billions or trillions of years, periods that dwarf the span of human history. It also reminds us of the contrast between transient brilliance and enduring structure. While her glow will fade, the crystalline lattice within, the diamond star itself, will persist as a frozen monument to the physics that governs the cosmos. Lucy's destiny as a black dwarf is a final chapter that combines silence, invisibility, and permanence, transforming her from a luminous marvel into a quiet, enduring symbol of the universe's capacity for both beauty and endurance. In essence, Lucy's future is a story of patience and transformation. She will continue cooling for billions of years, gradually fading from view, yet maintaining her structure as a moon-sized diamond floating silently in space. From a glowing, observable jewel to a hidden black dwarf, Lucy's journey is a testament to the inexorable flow of time, the power of gravity, and the resilience of matter. Even when invisible, she will remain an extraordinary relic of stellar evolution, a cosmic diamond that silently preserves the memory of a star that once shone brightly, a reminder that the universe holds wonders that endure far longer than light itself. As we look back across the incredible journey of Lucy, the diamond star, it becomes impossible not to feel a profound sense of awe at the sheer scale and beauty of the universe. From her origins as a massive, blazing star to her current state as a crystallized white dwarf, Lucy embodies the full arc of stellar evolution. She is a testament to the patient, relentless forces of the cosmos: nuclear fusion, gravity, cooling, and crystallization, all combining over billions of years to produce something simultaneously scientifically extraordinary and breathtakingly poetic. Unlike anything we could craft on Earth, Lucy is a diamond of cosmic proportions. 4,000 kilometers across, denser than we can imagine, and glowing with the energy of billions of years of stellar history. The story of Lucy is remarkable not only because of her size or composition, but because of what she teaches us about the universe. Her carbon-oxygen core, crystallized into a perfect lattice, provides tangible evidence for theories about white dwarf cooling, astroseismology, and the life cycle of stars. She validates decades of astrophysical predictions, acting as a cosmic laboratory where human curiosity meets nature's incredible precision. Even her pulsations, subtle vibrations imperceptible without advanced instrumentation, carry the secrets of her inner structure, showing that the universe communicates in ways we can learn to understand.
Through these signals, Lucy has become more than a distant point of light. She is a bridge between imagination and scientific discovery, a lesson in both scale and elegance. Beyond her scientific significance, Lucy is also a symbol of perspective. The human mind struggles to grasp numbers like 10 billion trillion carats, or the fact that a teaspoon of her material would weigh several tons. She reminds us that the universe operates on scales far beyond our daily experience. Yet, even within these extremes, there is a remarkable order and beauty. Lucy is a crystallized monument to time, matter, and energy, proof that even in death, stars can leave behind something awe-inspiring. The processes that formed her, from the fiery fusion of her youth to the slow crystallization of her ancient core, are natural, yet miraculous, emphasizing that the cosmos has its own artistry, operating silently across incomprehensible distances and eons. Her connection to our sun adds another layer of wonder. In 5 billion years, our star will follow a similar path, eventually cooling into a white dwarf and ultimately crystallizing like Lucy. This link between the distant past of a star in Centaurus and the future of our own solar system is a reminder of the universality of stellar life cycles. Lucy becomes, in a sense, a preview of our cosmic destiny, showing that even ordinary stars, like the sun, participate in extraordinary processes. Her existence bridges human imagination, astrophysical theory, and cosmic reality, illustrating that the universe holds structures and phenomena of unparalleled scale and complexity, waiting to be observed, measured, and appreciated. Lucy's ultimate fate as a black dwarf, silently drifting in the void, transforms her into a quiet testament to endurance. Even when she no longer emits light, her crystallized diamond core will persist for trillions of years, a monument to the forces that shaped her and the long-term resilience of matter under extreme conditions. She embodies the paradox of impermanence and permanence. While her glow is temporary, her structure is enduring. While her formation took billions of years, it will persist far beyond the current age of the universe. Lucy demonstrates that beauty in the cosmos is not always immediate or flashy, but can exist in subtle, enduring forms that reveal themselves over immense scales of time and space.
In the end, Lucy inspires a sense of humility, wonder, and curiosity. She's a moon-sized diamond, dance beyond comprehension, pulsating with a hidden rhythm, glowing with the energy of billions of years, and destined to eventually fade into invisible eternity. Yet despite her distance, her silence, and her immense scale, she speaks to us about the life cycles of stars, the incredible laws of physics, and the timeless artistry of the cosmos. Observing and understanding her allows us to appreciate the grandeur of the universe, to marvel at forces that operate across unimaginable spans, and to feel the emotional resonance of a star's journey from fiery youth to crystallized maturity. And so, as we imagine Lucy drifting silently through the constellation Centaurus, crystallized and glowing, we are left with a simple, profound truth. A diamond the size of a moon shining quietly in space, a reminder that even stars leave behind something beautiful. In that quiet brilliance, the universe whispers its secrets and its poetry, showing us that science and wonder are inseparable, and that even the remnants of stellar death can inspire awe, reflection, and inspiration across the vastness of space. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.